What page is that?
219. So I don't really get the whole, so in order for something to be conductive,
No,
no?
no, it's not about conductive. You're just trying to determine if you're looking at an ionic compound or a covalent compound. That's what it sounds like to me.
Yeah, no, beyond that now. Okay. That's better direction. Um, okay, so in order for an ion to be positive, they have to be metal. Or could like lithium lose a couple electrons and then become negative?
Okay, well, hold up a second. What, so first off, do you have a periodic table?
Yeah.
So lithium's element number 3.
Yeah.
So what does that mean to you?
That means it has one valence electron. It has 3 protons.
Okay.
And it has an atomic mass of 6.94. Okay, and then this is my other question. So if it has an atomic mass of 6.94, does that mean that it's more inclined to gain electrons than lose them?
No. Its mass has nothing to do with its ability to gain or lose electrons.
But I thought that was an average.
Of its mass, yeah, of all the different isotopes of lithium. Doesn't have anything to do with the number of electrons.
Electrons have mass though, right?
It's so insignificant when an atom loses it, we don't account for it.
Okay. So I don't...
Hold up. I asked you a question and you shotgunned it, which means you threw everything you knew about it and didn't actually answer the question. Does that make sense?
What does lithium mean to me?
No, what is lithium being element number 3 mean to you? It means it has 3 protons.
Okay, yeah.
And that, since it's an atom, it means it has 3 electrons. Okay?
Not necessarily.
Yeah, necessarily. It absolutely has to.
Okay.
If it's an atom. That's what I asked you, the atom. What is it being element number 3? So the atom has to have 3 protons and 3 electrons. And the elements on the periodic table that are considered metals, one thing about being a metal is that you give your electrons away. All right, so you said something fundamentally wrong a moment ago. You said, well, if I was a lithium and I gave 2 of my electrons away, could I become negative? What charge does the electron have?
Positive?
No, that's what the proton is.
Right.
So if you gave away something that was negative, what happens to your charge?
You become more positive.
Yes.
Okay.
So you said lithium gives away 2 electrons and becomes negative. No. If it gave away 2 electrons, which it can't, if it gave away 2 electrons, it would have a +2 charge.
Okay.
Because it gave away 2 negatives, leaving behind an unequal positive negativeness, leaving a net +2.
Okay. I think I'm getting a little bit turned around in the whole positive negative alignment.
So the nucleus is where the protons are, and the protons are the positive thing. And since the nucleus can't change, then it's always got an inherent amount of positiveness. The only thing that can change are the electrons. You can either lose some of your electrons or you can gain somebody else's electrons. So you can get rid of negativeness or you can take on negativeness, and that determines the ion's charge. So if I'm a lithium, you said earlier you have 1 valence electron. What that means is lithium will give that 1 electron away.
And just not have any valence electron?
Correct.
That doesn't, I'm having a hard time getting that.
All right, one sec. We had this discussion when I put up a picture of Minas Tirith from the Lord of the Rings. All right, let's go. Oh, sorry. Let me share screen 2. Go here.
Where's your face? All we see is your family. I feel like that means you're like in your bathrobe.
Not at 6:10. No. No, it means I have to click extra button to do that, and I never remember to do that. All right, so if you see 3 protons, I got to be talking about lithium, right?
Right.
By definition, anything with 3 protons in its nucleus is lithium. So
Okay.
the way the electrons work is the first 2 electrons go in the first energy level. So there's an electron and there's an electron. And then the next 2 electrons go in the next energy level. The problem is lithium only has 1 more electron.
Mm-hmm.
So what lithium wants to do is get rid of that electron or gain 7 electrons. So what do you think it's going to do?
Get rid of it.
That's what everybody in column 1 looks like. Its last electron is in an energy level all by itself. And what the elements are trying to do is, this is 2 protons. What element is 2 protons?
Helium.
And what do you know about helium's chemical reactivity?
It is a noble gas.
So what's that mean?
It's not reactive.
And everything in the universe is trying to become unreactive.
Yes.
So if the lithium atom can take this electron and get rid of it, what does it have left?
2.
It has 2. And who else has 2 electrons?
Helium.
And is helium reactive?
No.
So that lithium did what it wanted to do, which was to become not reactive.
Okay. I'm trying to understand why that is. Why?
Why what? Why what is?
Lithium can have, I guess it has to do with that outer valence shell.
Yeah.
Yeah.
It doesn't want it.
It has an outer valence shell.
Yeah, it doesn't want the outer unless it's close to being finished. So we can look at it another way. So here's 9 protons. So we're talking about what element?
Fluorine.
Fluorine. Fluorine's missing an electron right there. So if it gets that electron, then it'll have 10 total electrons. And what element has 10 electrons?
What element has 10 electrons?
Yeah.
Neon.
Is neon chemically reactive?
No.
So if it gets that 1 electron, then it's done. It's good to go.
Mm-hmm.
So fluorine is trying to finish off and have a filled energy level. And in this case, the fluorine's easiest way to get that task done is to gain 1 electron. Lithium's easiest way to do that would be to get rid of 1 electron.
Mm-hmm.
So everybody in the fluorine column, they're all trying to gain 1 electron. And everybody in the lithium column is trying to lose 1 electron.
Okay.
That is what they're doing.
Elements that have the same amount of electrons, how do they relate to each other? Does that have any effect on their, wait. their electronegativity.
No, electronegativity is an inherent quality of an element.
And that doesn't have anything to do with where they are in the periodic table, or how many.
You've asked like 6 questions. So which one do you want me to answer? Which one do you want me to answer?
Any of them.
Electronegativity is an inherent quality of an atom. It has a certain amount of electronegativity, period. So if I'm a carbon atom, I've got an inherent electronegativity of 2.55, period. That's it. I am stuck with that amount. If I'm a fluorine, I have 4.0. If I'm a hydrogen, I have 2.2. What that number means is its ability for that atom to grab an electron. If I'm lithium, I'm like 0.7 or something like that.
Right.
The bigger the number, the better I am at taking electrons away from stuff. Fluorine's got the biggest number. So what's fluorine able to do? Take electrons away from anybody except for the noble gases. Francium's got the smallest number. So francium is the element that cannot take electrons from any atom. It will give electrons to anyone. And fluorine can take from anyone. So anybody in that fluorine column is very good at taking electrons. You can see they have relatively high electronegativities.
And fluorine is better than chlorine because
it's smaller. The nucleus is closer. So what is this? What's this fluorine here trying to do? What's this guy right here trying to do? Grab one electron, right?
Right.
The thing that's doing the grabbing is the 9 protons. Okay? So it's very close to the nucleus. Chlorine, on the other hand, has 17 protons. So it's got electron. The electrons are further away from the nucleus. So which planet does the sun have the best hold on? Mercury. Why? Because it's right next to it. Which planet does it have the least amount of hold on? Pluto, because it's furthest away. So the further you get away, the harder it is for the nucleus to hold on to those electrons. And if I'm trying to fill a hole and it's far away from me, I'm not very good at it. I'm only relatively good at it. So if you look at the electronegativity values, which, where are they? Well, if you use the periodic table that they sold at the periodic table that they sell in the bookstore for $1, it just shows you that the electronegativity in that column drops precipitously as I go down the column.
Mm-hmm. Okay.
So if I'm looking at 2 atoms and I compare their electronegativities, whichever one has a bigger electronegativity is going to be taking electrons from the other atom. Yep, that table there. There's a green number on the back side, and for fluorine it probably says 3.9.
Yes.
Biggest number.
Okay.
The next biggest number is actually oxygen at 3.5.
Okay. Yes.
So those 2 atoms are the best atoms at taking electrons away from stuff.
And then nitrogen.
Then I think it's chlorine, actually, at 3.16, right below fluorine.
Right. Okay. All right. And then these atoms don't bond, they just stick together.
Which ones?
Next to each other.
The ions?
Yes, the ions.
Correct. So if I was this lithium here that became lithium with a plus charge, and I came somewhere near a fluorine with a negative charge, they would just sit next to each other because you're a positive ball and you're a negative ball. In the same way that if you put 2 magnets next to each other, they just hang out next to each other. They stick to each other, but they're not like connected to each other permanently.
Okay. They're like best friends, but they're not married.
Sure.
Okay. So these differ then from, so a lithium and a fluorine ion differ from a lithium and fluorine atom in a covalent bond.
No such thing exists. They can only connect to each other in an ionic fashion. Covalent compounds can only be found between nonmetals and nonmetals. Where's that page?
Yeah, I remember that.
There's like blue and green and pink, the periodic table.
Okay. Yep. Right.
So let's talk about that for a second. Why? So go grab that periodic table and look up lithium's electronegativity.
In green, 0.98.
So if the difference between these two numbers is bigger than 0.5, then the bigger one takes. So this number is this difference between these is much bigger than a half. So that means the electron is just shifted and given to the fluorine. Lithium has no possession of it whatsoever. It doesn't want it. If I was talking about a covalent bond,
because it's metal.
No, remember the reason that it didn't want it is this picture right here. It wants to look like helium, right?
If it's an ion.
So it wants to give away the electron. It wants to desperately. Lithium cannot be found in nature as an atom. That's how chemically reactive it is. When we find lithium in nature, it's given its electron away. And it gave it away billions of years ago because it never wanted it in the first place. Every night you piss off lithium.
When you plug your phone in.
When you plug your phone in. Because what are you doing? You're shoving that electron back on the lithium and it's like, damn it, I just gave it away. And then the next day it gets to give it away only for you to put it back on at night.
Okay, so that lithium is then combined with a base.
Whoa, stop. Why are you talking about a basis all of a sudden?
How do you make a battery?
You just need something that will take electrons away from, will accept the electron from the lithium.
So anything
that will accept electrons.
So are batteries, do they have liquid in them, or how does that?
Most of them have some kind of liquid in them. Even the the dry cell batteries, which are like your AA batteries or your D battery or your AAAs, there's still some dampness inside them, which is why they don't last forever, because the water will eventually evaporate out of there and then it won't work at all. Inside that battery, though, it's zinc atoms giving electrons to carbons. And then the zinc gives 2 electrons, and the carbon becomes -2, and the zinc becomes +2. And those are the electrons that are doing stuff for you. So if you've got a battery inside of, say, a remote for your television, this is what's going on.
It's zinc.
It's zinc metal giving the can itself, that is the battery, has a can inside of it that's made out of zinc. And then the reason that there's a little nub on the plus side is there's a piece of graphite that runs down the center, and it's exactly the same stuff that's inside of a pencil. Mm-hmm. And so the electrons leave the zinc out the bottom of the battery. They run through the remote, and then they enter the battery at the top where they connect to carbon, giving 2 electrons to carbon atoms.
What number is zinc on this periodic table?
It's in the D block. So that section that's down below, and so it's 29, or is it 30? 30? You see copper?
30, yeah.
Yeah, 30.
Okay. Okay. And so everything to the left.
Oh, there it is. The back cover, yeah. All this stuff. Did you highlight that orange?
Yeah.
All those guys, those are metalloids.
Yeah.
So everybody on the left of that gives electrons away. Everybody on the right takes electrons. Everybody on the right can make a bond with everybody on the right, but everybody on the left, they can't make bonds with everybody on the left. Metals don't make bonds with metals. They mix and form alloys, but they don't make chemical bonds.
And what does that mean if they mix and form an alloy?
It just means that when they get mixed together, that they have different properties. So copper is really soft, and you know what color copper is. And zinc is kind of metallic-y looking, and it's very rigid. And if you put those two things together, you get brass, which is harder than copper, but softer than zinc. And the other thing about zinc is really easy to corrode, and copper is not. So then the brass is not easy to corrode. So you get properties of both of those things, making what you make better than either of the originals. I guess it depends on what you mean by better.
Did you say they don't mix?
No, I said they do mix. They don't make chemical bonds, though. They just mix.
And what is that?
What do you mean, mix?
Yeah.
I mean, exactly. There's nothing weird. It's just the word mix. Nothing else to it.
Oh.
You take chocolate chips and put them into cookie dough.
Mm-hmm.
Same thing. That's mix.
Okay. 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 Oh. Great. Okay, and then the polyatomic ions.
Polyatomic ions are just covalently bonded compounds that have an uneven number of electrons and protons. So the easiest one to talk about is going to be hydroxide. So this is what most people consider to be a base. So this polyatomic ion, hydroxide, basically what's happened is one oxygen and one hydrogen have come together and stolen one electron from someplace else, and we don't care where. Doesn't matter. So this guy comes with 8 electrons, and this guy comes with 1 electron, and together they stole 1 more electron. Again, doesn't matter where they got it from. So I've got an oxygen and a hydrogen, and this is a covalent bond.
Okay.
But since they stole an electron, this thing here is an ion. So when it forms a bond with, say, lithium and makes lithium hydroxide, this is ionic. This is an ionic substance because this thing here has a negative charge and this thing here has a positive charge. The oxygen and the hydrogen could have stole the electron from the lithium. Doesn't matter. And so that's the same situation with all the polyatomic ions, like NO3 negative. These 3 oxygens and that 1 nitrogen have stolen 1 electron from somebody else.
All right. And you know that somebody's stolen something.
Because this has a charge. It's written -1 here. So that charge came from somewhere. If it wasn't charged and it just said NO3, then this would be a covalent molecule, nitrogen trioxide. But it's not because you see the negative sign there, so that's telling you that it's a polyatomic ion, which just means that it's an ion that's got lots of atoms. And you treat it as one object.
Oh, okay. And then... All right. This list on table page 220.
Yep.
On common polyatomic ions, most of these are just 2 atoms create. So these 2 atoms create a single ion. Is that right?
Yep.
Okay. And that single ion doesn't have a positive or a negative side. It just is positive or negative.
Correct.
Okay. And these are mostly just 2 atoms that have come together to do this. Is that kind of generally how that goes?
Two, you mean not? Yeah, pretty much.
Yeah, so there's acetate and bicarbonate. Those are the only.
If you're going to take the Chem 121 class, this is one of the first things that you memorize. And it's a short, it looks long, but it's a short list of polyatomic ions. And you need this so you can name stuff.
Okay.
So again, most of them, you're right, are two atoms of varying numbers, but then you also have three atoms, like the hydrogen sulfate, or the hydrogen phosphate, or the hydrogen carbonate, or the acetates. So it doesn't have to be two, and it doesn't even, it could be three, it could be one. Bottom right hand corner, just above that, is mercury 1.
Yeah.
So there's just one atom there,
Okay.
or atom type, two atoms, both of the same atom element.
All right. And then that moves on to aqueous solution.
Sure.
So I get that the this little swirly J looking thing with the positive or negative next to it, what's that sign?
That's the lowercase letter delta, and it means partial in chemistry and in math. So it's a partial positive, not a full-fledged positive charge.
Okay, and that has something probably to do with the shape of that then, I'm asserting.
Yeah, we talked about this when we talked about things being polar and not polar.
Yeah,
So oxygen has an electronegativity of 3.5, and hydrogen has an electronegativity of 2.2. So because the difference is greater than 0.5, but is smaller than 1.9, that makes this bond here polar. So what we mean by that is this bond that's right here, this is actually 2 electrons. That's what the line means. Sorry, I didn't write a hydrogen there. These 2 electrons are what are holding the hydrogen and oxygen together. Okay? So what you would expect is them to be even on each side, the hydrogen and the...
Right, but because of the number of electrons?
No, because this number here is 3.5 and this number here is only 2.2, the electrons spend much more time around the oxygen than around the hydrogen.
Okay.
So that makes this side look kind of negative, but only partial negative, which makes this side look partially positive. So now water runs around and it has this shape, this bent shape, where one side of it is negative and one side of it is positive. So then the negative stuff, let's say there was a lithium positive floating around, the oxygen would be attracted to that.
Mm-hmm.
And if there was, say, a hydroxide floating around in the water, the hydrogen on the other side would be attracted to this hydroxide because it's negative. So when table salt goes into water and dissolves, it's because the NAs get grabbed by the oxygen side of water, and the CLs get grabbed by the hydrogen side of the water molecules, and they form an intermolecular force where there's an attraction between them. It's there's more. There's going to be a whole bunch of water molecules actually around this sodium.
So there's a lot of attraction there.
Yep. And so this sodium is considered aqueous because it's surrounded by water molecules.
Mm-hmm. Okay.
So you can see that in that picture on page 221, where the sodium is surrounded and the chlorine is surrounded. And the cool thing about that picture is it shows you how the hydrogen side flips over when I'm talking about chlorine. That's why water is the universal solvent, because it can interact with both positive things and negative things, and it's tiny.
Yeah.
It's like nature's little knife.
Nature's little knife.
Yep, it goes in and breaks things apart.
Okay, so that oxygen having that electronegativity of 3.5, these other elements that have higher electronegativity also, do they have the ability to become polar? I was thinking it had to do with the number of atoms in the.
No, it's got to do with the whatever it's connected to.
Okay.
So if it's connected to something with a lower electronegativity, then it can be polar, and that's it.
Okay.
It's got nothing to do with either atom's mass, has nothing to do with the number of electrons that either one of them have. It's all about if one of them's got a larger electronegativity, a significantly larger electronegativity than the other atom that it's bonded to.
All right. That's a lot easier than I was making it in my head.
Well, that's good. Sam, did you have a question?
Then I was just gonna hop in and
Okay.
see what everybody else had to say.
All right. Bethany, did you have something you want to type in chat?
So my husband went on his first mountain bike ride.
On his new bike?
What?
On his new bike.
Uh-huh.
How'd that go?
And
He fell off
broke.
Syncline? Oh,
No,
well.
something broke. No, not his body, his bike. Something on his bike broke. The crankshaft, I believe, or something.
Bottom bracket?
Shared. The what?
Bottom bracket?
No, it's where your pedal goes in and you like it got stripped basically.
Oh, he'd go to pedal and it would just spin and do nothing.
Well, he didn't realize that until like he was going about to go down a hill and he went to put his foot down or something and his foot went all the way down. He's like, what the heck? And his pedal was on the trail.
His whole crankshaft was on the trail then, or just his pedal.
Just his pedal was on the crankshaft. So when he got home, or when he got back to his truck, he realized, I mean, he's really good about bikes, so he didn't think this was his error, but for some reason the warranty is not going to be on his side.
So they're saying he put the pedal on wrong and he stripped out the crankshaft thread,
where
the thread where the pedal goes in.
Yeah.
Another
$110 to get that fixed, and he's like super bummed. So
he can't just rethread it. Use a tap.
I don't think he can do that. I don't know if he's able to do that. He hasn't said that out loud yet. I mean, but I don't know.
Well, he should be able to retap it with like a $20 tapping tool if he didn't mess it up too bad. But that was probably terrifying, having no pedal to stand on going down a hill.
He didn't get too far down, thank God. I mean, he could have been going down some like gnarliness, whatever, and hit a rock, whatever, just knock on wood. It could have been a lot worse, you know. So he was really bummed about that. So it was like my first ride, and this happened, and we expected. Was he going downhill? Was the vehicle downhill from the incident? Yes. That's good. At least it didn't include a walk in your bike shoes. Yeah. Everybody was asking what happened. They're like, "Oh, how long have you had the bike?" He's like, "It's my first day riding it." He was like, I'm almost in frustration tears because I have been waiting so long to actually ride this bike since I got it, and my first ride, so he'll figure it out. It's still early in the season, so he didn't hurt his body. It's just a bike, So he could have been calling me from the hospital, but he didn't. So I just prayed that he didn't get hurt. So that's all I could have asked for. I should have prayed that his bike didn't get hurt, but I just prayed that his body didn't get hurt. So, but yeah. He did get to go on one run down the hill. I think he went on Stimson Climb. I think that's what it's called. He did one run on it, and then he was on his way back up and about to go down. The second time is when that happened. So he at least got one run on the trail to get a feel for it. He absolutely loves his mountain bike. So
I don't think that made him feel much better.
yes. And then other exciting news for him is he applied for a new job out in Odell at a CNC shop. That's like what he went to school for, was CNC machining, and he works logistics right now at the aluminum plant, which he's not super happy about. So when he saw the job posting come up for the journeyman position, he had a mini panic attack, and he's like, "Oh, I have to have this job." So hopefully sometime this week he'll find out if he gets it or not. So
Well,
good
luck with that. He won't be riding his bike to work though.
No, we'll have to get him a little commuter car, unfortunately, but he's gonna be happier in what he's doing. So
that's all that matters.
Paper pushing and not being happy at his job. He needs to be working with his hands. He's that kind of guy. He needs to work with his hands, create stuff, design stuff, and doing logistics in a front desk is not where he's meant to be. So
gotcha.
Yeah, I'm praying that he gets this job. So even though he won't be just riding his bike to work a mile commutes, this is going to be a really, really good opportunity for him. So the company is growing immensely. So we're hoping that he gets this. So that should be nice. Nice for both of us. So yeah, I didn't really have any questions. I almost forgot about it, writing some stuff down. I'm like, oh my god, it's 6:06. So want to hop in and see what y'all are doing.
Did you have more, Sarah?
Yeah.
What you got?
So on page 249, figure 6.4 is a measure of pH.
Yep.
And so to the right is more
basic.
Mm-hmm. And the other is more acid.
Acidic, yeah.
Acidic. And alkaline is in the middle. Yeah.
No, alkaline means basic.
Oh, okay.
It's just another word for basic.
Right. My brain is really.
Neutral. That's what's in the middle.
All right. Neutral is in the middle. So I many years ago worked in home care, and if with developmentally disabled adults.
Okay.
And if they went 2 days without having a bowel movement, I had to mix them up a little cocktail of milk of magnesia and prune juice.
Yeah.
Fruit juice.
Oh yeah.
Yeah, milk of magnesia is just like taking a magnesium supplement. If you take too much of it, like 500 milligrams or more, you get really bad upset stomach, and you'll definitely have the
Diarrhea.
diarrhea at that point. But you know, if you do a little bit of it, actually helps you sleep, and it's a really good.
Muscle relaxer.
Yeah, I take that when I have a lot of back pain. So there's also a topical magnesium too that is really good if I have like a
Epsom salt.
back or an Epsom salt bath. Yeah, that's amazing.
So is it a diuretic or is it a muscle relaxer?
It's both.
Yeah.
The fact that it is a muscle relaxer automatically makes it so the bowel muscles loosen up and allow you to go.
Okay. I was curious about the chemical function of that.
The magnesium is something that allows the muscle to relax. The cells of the muscle, it allows them to let go of a contraction.
Okay.
So that's something that you were probably given, whether you knew it or not, after you gave birth. They probably just called it MAG. You were probably on a MAG drip.
Okay.
So you had all of those muscles working hard, and they don't tend to relax very quickly. So they'll put you on a magnesium IV drip to allow that to happen more rapidly without giving you any narcotics, so you don't have to dope up a newborn.
Okay. Nice. So what causes something to be more acid than alkaline? And are there general rules?
Certainly, it's a little bit more complicated than what I'm going to say here, but for this class, it'll be fine.
Okay.
A guy named Arrhenius came up with this a long time ago when he was studying dyes. And so the very first theory of acid bases is based off of this. So,
And it's since become more complex.
yep.
Okay.
If in some water you have more H pluses than you have OH minuses, you have an acid. If you have more OH negatives than you do H pluses, then you have a base.
Okay. Why is that?
Because it is. I don't know. I don't know how to, because that's the way it is. That's what an acid is. If you have a cut on your mouth and you eat some tomato sauce or a salt and vinegar potato chip or a lemon, the thing that attacks the nerve ending is this.
In any kind of combination? So if you've got
No, it's just that. Just that right there.
Okay. Okay.
It isn't more complicated than that. So if you add something to water and the amount of these things goes up, then that thing that you added was an acid. And if you added something to water and the amount of this went up, then that thing that you added was a base.
Right. I would like to know how molecules come together to actually form things.
I'm not sure what
What's
that
the,
what
what's
that
the
means.
easiest way to wrap my head around that?
I don't know what you mean by that.
Well, um, so molecules come together to form cells.
That that's a big thing you're talking about now. That doesn't have much to do with this class.
Hmm.
That's a biology question.
Okay. So, how does chemistry make up the human body?
How does what? Oh, chemistry make up the human body?
Yeah.
Uh, well,
Chemistry is pretty much like the smallest
well,
breakdown of everything.
an example would be every cell is a has a lipid bilayer.
Yep.
There's water inside the cell and there's water outside the cell.
Mm-hmm.
Fat.
Yep.
So you have fat, one end of the fat. So this is um, so this side of the fat here likes water. This side likes water. So when I'm looking at this lipid bilayer here, this is on the outside of the cell and
Yep.
this is on the inside of the cell. And everything that's in the middle here is fat.
Okay.
So that allows you to have water on the inside and the outside. If I just had a layer that was just one layer thick, then the inside couldn't have any water in it.
Okay.
So there you go. There's some chemistry. I have a bunch of these things next to each other.
Yep. What are those made out of?
Those are fat
And fat is its own
molecule.
molecule?
Yeah,
Oh. It's not called fat though. What's it called?
a lipid.
Lipid. Yeah. Okay. All right.
Where cardiovascular disease comes from. Too many lipids.
No, no,
No?
no.
I'm thinking of something different.
No, you're just saying what people say, which
Yeah, I know.
is just wrong because nutrition has been wrong for 100 years.
So where does it come from then?
The sugar industry. The sugar industry. I'm not joking.
Yeah, I buy it.
100%. They decided to say, hey, let's blame all cardiovascular disease problems on fat, and then they'll ignore us. So, are peanuts bad for you?
If you eat like a pound, they're really bad.
Okay, that's you can't say that.
Yeah.
5 gallons of water will kill you. So is water bad for you? Of course
Right.
not. Are peanuts bad for you? Would that be a bad snack food?
No.
For a long time, the sugar industry made it out to be like peanuts were bad because they had a lot of fat in them.
Mm-hmm.
So when you eat sugar, what's sugar good for?
Energy.
What else? Nothing.
Yeah. Okay.
So what does your body do with excess sugar? It makes
it's
fat.
Yeah.
It makes adipose tissue.
Right.
When you eat a peanut, what will the fat in the peanut be used for? To increase your cholesterol levels and cause you to have heart disease? The answer is no. It's this right here.
Uh-huh.
This stuff here that makes up the interior portion of the cell membrane,
Right.
that's what it's used for. Could it be used for energy? Yeah, but what's your body going to do with it? It's going to build stuff. So
diet, or it's gonna get ready to build stuff.
if you had some wood, what could you do with it?
You could build with it, or you could burn it.
That's fat. Fat could be used for energy or it could be used to build stuff. What's sugar? Sugar is like charcoal briquettes. Can you build anything with it? It's good for one thing and one thing only. It's good for energy. Wood is good for energy and structure. Fat is good for energy and structure. Nobody talks about this stuff.
Mm-hmm.
That's where like the keto diet comes in now, right?
Sure.
Because it's like mostly fat and no carbs, or like no sugar.
No sugar. Yeah, it's just no sugar.
Well, keto's all fat. The dangerous thing about the keto diet, though, is that most people aren't really all that capable of cutting out sugar to that degree, and then they just end up on like they end up cheating, and then they've got all this fat in their system, and then they throw the sugar on top of it.
Okay, didn't we just get done saying fat's good? And then you made it bad.
Even not too much fat, though. Even too much fat without the sugar is still gonna be. That's still gonna be running through your blood system.
Here's the problem. You can't eat too much of it.
Are you thinking about like fast food or something, Sarah? Like that kind of fat, or like?
Because fast food isn't fat. Fast food is sugar.
Well, okay,
Fast food is, well, and it's hydrogenated.
None of that matters.
Hydrogenated fat doesn't matter?
Not anymore. Now that they fixed the catalytic problem.
So even if it's hydrogenated, it's okay?
It doesn't really matter. That's not something you should worry about. Like you're being gaslighted by the sugar industry when you say stuff like that, because it doesn't matter. What matters is the fact that the bun is almost 100% sugar.
Right.
What matters is every single thing they sell at McDonald's, with the exception of black coffee and Diet Coke, has sugar in it. Everything. There isn't a single thing you can purchase except those two things that don't have sugar in it. You might think, well, French fries. The French fries are soaked in sugar before they're cooked.
And salt, which is why they're so delicious. Sugar, salt.
Yeah, but you don't need it. You go to other places that sell you French fries, you love them too. They haven't been pre-soaked in sugar.
Yeah. I actually really like potatoes a lot much. They kind of make me feel sick.
Well, not sweet potatoes.
It's all the starch.
My husband is doing keto, and it's very hard to cook meals now.
We eat a lot of cabbage.
I love cabbage. I love kraut.
All those cruciferous, sulfur-producing vegetables.
Yeah. My house, if you light a match in my house, it'd probably blow with the amount of cruciferousy gas going off my house. My husband. The keto diet is like extremely strict with what's eat. Literally, it's no sugar, other than half a cup of berries, which still has sugar, but it's a natural form of sugar. It's not added sugar or like processed sugar. So meats, cheeses. Vegetables. We used to eating pastas with anything. It's,
Zoodles.
All about the zoodles. Love the zoodles.
Something else, Sarah?
Question?
Okay. I prefer that answer.
Okay. I'm gonna go check on some baby chicks.
You have baby chicks?
40.
Oh my god.
Yeah.
How many chicks do you have right now though before the baby chicks?
12.
Are you raising meat chickens?
Just
Like
eggs.
egg chickens?
Yeah.
Oh, dang.
We lost 34 of them in 2 minutes to a husky that attacked over the summer.
Oh, exploding chickens. That's the worst.
What?
We had dogs eat our chickens too.
Oh, I don't know why you're saying exploding.
Well, I guess our chickens were bigger than chicks. But we came home on a number of occasions to what looked like exploded chickens
Oh.
in the yard.
Yeah, he didn't even do that. He just one bite around the neck, one wriggle, and then dropped it and went on to the next one. They just looked like they were laying on the ground. Yeah.
Were you there?
Nope. Neighbor saw it.
You know whose dog it is?
Yep.
That's so hard.
All right.